Yay. Stability is a keyword. Stay. It's supposed to be shatterproof, but I don't want to test that. Alright, guys. So any questions from homework? Yeah. $15, 2, 3? Yeah. All right. Crouching limits hidden math. Somebody who's writing you can read. That's jealous of that. All right. So this one says this is 15.2.3. The limit as t goes to 3. Stuff. 15. T squared minus 9 over 2t squared plus 7t plus 3. Oh, I like this problem. You would, Jeff. Oh, it goes to -3. There you go. All right. So it's not quite as good as I thought it was going to be. Oh, well. If it was this, can somebody tell me the answer very quickly? 0. You don't have to do anything. It's 0. The answer is 0 because the top is 0, right? At 3 and -3, the top is 0. Well, when you plug a 3 into this, you get something, not 0. So it's not indeterminate. What's the opposite of indeterminate? Determinate, which means you should be able to determine the answer if it's not indeterminate. So that would kick ass. Too bad for you this and this. Because I think when you plug a -3 in here, you get 0. But let's double check. What do you get? You get twice 9, 18, minus 21, it's -3 plus 3 is 0. Sure enough, you get that. So what's funny, though, is this is one of our least favorite kind of things to factor next to cubes. But you already know what a factor of it has to be, don't you? If it's 0 and -3, what must be a factor?
3.
Who to what? If it's 0 and -3, what must be a factor of it?
T3.
T plus 3, of course, right? In fact, that is a theorem from pre-calc about if the roots relate to the factors of the polynomial, blah, blah, blah. But it doesn't make sense. If it's 0 and -3, you better have a freaking T plus 3 in there to explain that. So then what must this be? 2t plus 1. 6t, 1t makes 7t. Or factor it like you're supposed to know how to. Either way. Or be smart and use something that's a hint. Right? How's the top factor?
T minus 3t plus 3.
And then you just cancel the problem. And once you cancel the problem, you can plug it in because there's no problem anymore. That's the fundamental idea of an algebraic analysis of a limit. If you can kill the problem, then there's no problem. Then you can plug the number in. That's really nice. If only life worked like that. Right? Kill the problem. You want the problem.
So the answer is 0?
Huh?
0?
I don't know. Oh, -3 minus 3?
0. Oh, -6.
-6 over -6 plus 1.
-5.
So it looks like 6/5 maybe.
How did you do that again?
The last step?
You just do that, yeah.
Oh, what was the very first thing we did? The very first thing we did. What was the very first thing we did?
Factor.
No. Before we did anything, we wanted to see if there was a problem. So I plugged it in. Because if it works, I'm done. If it doesn't work, oh shit, I got stuff to do. Right? And when I plugged the -3 in, I got 0 over 0 indeterminate form. In order to determine it, I have to change the form. Does that make sense?
Yes.
So once I change the form, now I can try to plug -3 in again. And see if I did manage to make it determinate. And I did. I took care of the problem. Yes?
Do you want if it's 6/5 or do you want it to be 1 over 1? 1 and 1/5.
Yes. They're the same thing, aren't they? For me, they're the same thing. Whatever way looks better to you. I slightly prefer 6/5 myself because it's quicker to say. But if you want to write 1 1/5, I can't. How can I argue with that? You're crazy. Half a dozen is 6. You're crazy. Sorry. You know, like, not a Bakersfield show. All right. Anything else from homework? Yes.
Can you go on 42?
My favorite number. In that same section?
Yeah.
Ooh, I like it. I personally think that absolute values should not exist.
Oh, yeah.
We should define them separately. But they do exist, and therefore we must know how to work with them. Too bad for us, we weren't around way back in the day. Why do I not like absolute values? Because an absolute value is actually two functions hiding in one. Do you understand what I mean?
Yes.
Because if it's negative, it does something. If it's positive, it doesn't do anything. So it does two different things. So that's kind of evil. And that's the whole point of this problem. The whole point of this problem, you see, I'm going to show you something, and even if you don't quite, I'm going to show you something, that's all I'm going to do. I'm going to show you what to do at the bottom. What is the absolute value of x plus 6? So, let's be smart about it. If x plus 6 is greater than or equal to 0, which means if x is greater or equal to negative 6. If x is greater than or equal to negative 6, then that's the absolute value of a positive number. And what's the absolute value due to a positive number? It does nothing. So it would be x plus 6. If x plus 6 is less than 0, or if x is less than negative 6, like negative 7, then this would be a negative number. What's the absolute value due to a negative number? And how do you do that mathematically? Multiply by negative 1. I love it. So then this would be negative x minus 6. And now do you see how that ties in? In order for the limit to exist at negative 6, what must be true?
They have to go to the same spot, right?
The limit from both sides. So if you're coming from below, you would use this. Because if you're coming from below negative 6, all of your inputs are negative now. So that's what you would put in place of here. If you're coming from above, you would use this. Does it make sense? Below negative 6, what is this? It's that. So that's the function you would look at for below negative 6. And you do the limit from below negative 6. From above negative 6, the function is that. So you do the limit from above negative 6. And you guys should be able to really quickly see, right? I mean, this is twice x plus 6 over absolute value of x plus 6. Do you see that? Right? So if it's this one, what's the answer? If you plug that in there, what do you get? If you plug that in place of this, what do you get? Negative 2. If you plug that in place of this, what do you get? Oh shit, so the limit's 2. From below it was negative 2, from above it was 2. So the limit does not exist at negative 6 because it doesn't agree from both directions. Shit, Jeff, you did the whole problem. I love this problem though, but now you guys got to figure out how to write down what I just said. You got to show me what the hell happens. Just do it. Just plug it in, and then say, well, it doesn't work. It doesn't go to the same place.
Do you want to draw the graph? Because that's what it asks me.
Does it ask you to do that?
Somewhat like that.
No. It's just find the limit if it exists. If you want to, you can. I don't see why you'd want to. But think about the absolute value of x. What's it look like? Very rough sketch. The v. This, by the way, oh my God. No, hell no, right? If they ask you to graph something, even a rough sketch, you still got to show me some kind of detail, right? Something. So this is just for me to talk about it. What's the slope below 0? And what's the slope above 0?
1.
I like it. So what happens right there? Weird shit. You don't want to be in this airplane if this is the plane. Because what happens right there is everybody dies. That would be infinite acceleration. It's like, oh, it's not good. It's very bad.
Going down.
Something like that. Alright, how we doing? Alright, I know I just went freaky, but that explains why that problem is a little freaky, because it does different things depending on what side of 0 you're on, right? In this case, 0 moved. It was translated, right? Maybe. But this is what you need to be able to do that problem. This information right there. Okay. Anything else from homework that I can only halfway explain?
57.
Oh yeah, good. This is freaky. I like this. This problem really, I like it. So this says if the limit as x goes to 1 equals 10, find the limit as x goes to 1 of f of x. Unfortunately, people do this problem incorrectly, and I don't blame you, because it sounds like a freaky problem. But the big idea behind this problem, in order for, what happens at x equal 1 that we know of? In fact, what happens at x equal 1? What do we get when we plug a 1 in? What do we get exactly? What do we get? We get f of 1, because x is 1, minus 8 over 1 minus 1. So, I really want you to think about this. In order for the limit to exist, I really get this. What do we keep doing? Well, I was able to do that very first problem we did, because I factored the top and bottom, and then I canceled the problem, right? So, if the limit exists, but the bottom goes to 0 at 1, then what's the top got to do at 1? It also, what's the top got to do? If the top goes to 7, what's 7 over 0? If it's in that form, it's infinity. We know better than undefined. It's infinity, right? If the bottom gets smaller and smaller, the whole thing approaches infinity. It just gets arbitrarily large. How are we doing so far? Really get this. I want you to get this. So the only way the limit could be something finite is if the top also has the same problem as the bottom does. Doesn't that kind of jive with what we've been doing? If I can remove the problem, then the limit will exist. I can actually plug the number in and get a number. If that does not have a problem at 1, then the limit should be infinity. But is the limit infinity? No, it's 10. What the hell? So therefore, what must f of 1 be? Basically, I've given it away here.
8.
Yeah, f of 1 has to be 8. So that the top is also 0 at 1. Whatever the function f is, it's got to be 8 at 1, so that you get 0 over 0. You get indeterminate form.
So the answer is 8?
Yeah, f of 1 is 8. That's it. That's it. So somebody help me out. I really want you to get this. If I told you, if the limit is x goes to 2 and I have an x minus 2 there, the answer will always be infinity. Always. Unless the top is also 0. Then you've got these competing extremes. Do you see that? We get that with limits. We get these competing extremes, and then we're like, so we got to really stop and say, what the hell is going to happen? So it's sort of like this. What happens to that as x goes to infinity? It goes to 0. So it's an extreme. But the minute I put something up top that has the same problem that the bottom does, the bottom goes to infinity, and the top was 1. But now they both go to infinity. So that's interesting now. Now there's not going to be an extreme answer. There's not going to be 0 infinity. It's going to be something in the middle. It's going to be somewhere where they kind of compromise. Right? You guys look at me all weird. Of course, we know this limit to be what? We know this limit to be what? 1. Remember this from pre-calculus?
Yes.
Right? If they have the same degree, it's just the ratio of the coefficients. Does that sound at all familiar? Right? There's 3 situations for vertical or horizontal asymptotes you could be in. Right? The more you remember from pre-calc, the less you got to do in here. You can stand on the shoulders of your pre-calc self if you remember your freaking pre-calc. If you don't, you got to prove it all over again. Oh well, too bad. Right? Because how did you do this the old-fashioned way? Didn't you divide by freaking x? Blah, blah, blah. 1 plus 1 over x over 1. What you do when x goes to infinity, what happens to this? It goes to 0. Does that look familiar? Yeah, that's what we did first, and then we got better. We realized, well, screw doing that every damn time. Let's just summarize the pattern in 3 basic things. If they're the same degree, it's the ratio of the coefficients. If the bottom's a bigger degree, it goes to 0. If the top's a bigger degree, it goes to infinity, slant asymptote, or oblique asymptote, depending on your weird-ass teacher. Maybe. But I love that problem because it really makes sure you understand. If I left that blank, you cannot tell me what that is. There's an infinite number of things I can put up here, so the answer would be infinity. But there's one kind of thing I could put up here, so the answer might not be infinity. Right? Somebody give me a function I could put up here, so the answer is not infinity. Oh, I love that question. Oh. The easiest one would be
X minus 2.
x minus 2. Then the limit would be what?
1.
1. Or x squared minus 4, because it's got the same problem, doesn't it? Do you start to see what I'm saying here? Because now you could do something and it won't be infinity. So if I just say this and said, what's going to happen no matter what I put on the top, people might say it's going to go to infinity. And that would be evil for me to say it like that, because it's a trick question. It totally depends on what you put on top. If it has the same problem as the bottom, the problem cancels, and they kind of agree somewhere in the middle. The answer's not 0, the answer's not infinity, it's something in the middle. Alright, cool. I'm a weird math person, I know, because I love big ideas. I actually really dislike details. I really do. I'm not a detail person. So that's why I talk about math a little differently than you might be used to. But I love the ideas that come along with it. Anyway, all right. Anything else from homework I can make sound worse? But that was a weird problem. If you look at that problem, you're like, how the hell am I supposed to know? Right? And I don't blame you for feeling that way, but it's a bigger idea problem. It's the idea of the top and the bottom having an issue at the same place. So how many functions could I put here and it would work? Well, how many functions are 8 at 1?
Endless.
A lot, right? Can somebody give me a function that's got an x squared in it, so when I plug a 1 in, I get 8? You can do it, come on. It's not this, right? It's got to have some
X squared plus 7.
I'm sorry, dude. Plus, x squared plus 7. I like it. Right?
Yeah.
You guys with me?
Yeah.
So now watch. All right. So all we did, we knew that f of 1 had to be 8, so you just came up with the function that did that, didn't you? Right? So if you weren't with me here, I've still lost you, but oh well. For those of you that are still with me, this is all extra stuff anyway. But watch, what does this become? This becomes f of x is x squared plus 7. What's x squared plus 7 minus 8?
0.
Minus 1 minus 1.
Oh, okay.
And what can you do with that? You can factor it, right? And the funny thing is, if I ask you for a cube, won't the same thing work?
Yes.
And then it would be x cubed minus 1, and you could factor that. Little dudes would cancel, wouldn't they? So you start to realize. So this idea of this problem is a big idea, and when you look at the problem, you're like, it's a little tiny problem. It should, I don't know, it should be easy. Maybe I just multiply by. No, you got to apply an idea to it. The idea is stupid important. I love using the word stupid as an adjective. You know, is it stupid or is it important? But the idea that if the top has the same problem as the bottom, so what we keep doing is that we factor so we can kill the problem, so that I can plug this stuff in, right? Okay. All right. I'm hopeful. I think I assigned another problem that was sort of like that one, but I can't. I don't know if I did number 58 or not. Oh, maybe I did. Anything else from homework? Yes?
2.4, number 2.
Oh, so we still haven't really done anything concrete in 2.4 yet.
That's what I think.
Yeah, so that's the focus of today. Anything else from anywhere else except 2.4? Okay. So let's focus on 2.4. Trying to figure out which way I want to attack this. Let's do this. All right.
I know which way I want to attack it.
So there's two layers to this. What are you talking about there, weirdo? There you go, cool. We're still going to be in the idea behind the problems here for just a minute, right? I'm going to try to show you a visual behind what we're going to do. So it's going to be more concrete, it's going to be visual, that's nice. And then we're going to get to the more abstract, the actual proof itself, right? But let me pull up the, which one was it that ended up working? I can't remember now. Was it stupid Internet Explorer? I think it was. Yeah. No, I don't want to make Internet Explorer my default browser. Alright, that was, there we go. Okay. So I just want to pull this up. They got some nice animations in here, with which, you know, understandably does a lot better than any pictures I try to draw. Alright. So this is section 2.4 up here in the ebook. And here it is. Here we go. Alright, so here's what we've been talking about. And up here. Up here. Yeah, we haven't been talking about a box. Come on. There you go. Yay.
It did it.
There you go. Can you guys see that all right?
Yes.
Okay. Yeah, if I zoom in, it doesn't really grow. So I have a function. This function is in purple. That function going through there. And I'm curious about c looks to be 5, right?
Yes.
So this is a nice function. This is obviously going to have a limit there because this function is what through there? It's continuous, right? So if a function is continuous, that means the limit exists everywhere that is continuous. That's kind of nice. Continuity is kind of a big, a strong skill, a strong thing for a function to have. Right? Skill, that's awesome. So if that really is the limit, then it's got to get close to it. So all this whole thing we're going to do is just formalizing what close means. So if somebody says, I want you to be within 1 of the limit, then I can use these, don't these inputs, now I really want you to see, what's 1 away from that? Here. And so that input, isn't that 1 away from that limit?
Yeah.
Yes.
Do you see how this works? So obviously if they want me to be closer to it, if they want to make it more restrictive and say, no, I want you to be really close to it, then what's going to happen to these?
We're going to get closer.
They have to get closer, don't they? So if I want this to be like this, then I'm going to have that be like that. So this is my epsilon. This distance here is my epsilon. Epsilon defines how close the outputs are. Delta defines how close the inputs have to be to make that happen. Yes, sir? Oh, yeah, thank you. I need to hire. I keep saying I need to hire somebody.
I'll do it. Do you get paid for it?
You would. TA hours, but I'd make you grade stuff too, so. Not my class, too bad for you. I did great again, John. So if I make my epsilon get smaller, then see how, of course, I mean, on one level this just makes sense. I mean, concretely it makes almost too much sense, because then when you do the proof, you're like, well, how does this really? Well, I'll try. So obviously the closer somebody, no matter how close somebody wants me to get, I can always find inputs that make sure that I am that close. If I had the wrong limit in mind, so if I thought the limit was, I don't know, if I thought, ooh, do I have a laser? That'd probably be bad for us, but it looks like I don't. They don't trust me. Man, no laser. All right, sweet. So if I thought the limit was right there, right now I couldn't really tell, right? But at some point, they're going to want me to get, this is hard to do on this, but at some point that little green box is just not going to do its job. It's going to, I don't want to say this. So if I thought the limit was here for some reason, then there's no way I can always be closer and closer. It's getting closer to something else. It's going to be outside of that region. Does that kind of make sense? So if I have the right limits, no matter how close somebody wants me to be, I can always make my inputs interval so that it stays that close as the outputs. That's the idea. So part of your homework, let's do a specific example. Let's try to do, actually let's do this. If you have a calculator, we're going to use that right now. I'm going to show you, because part of your homework is going to be concrete. Alright, so I'll use the same function. And actually, we're going to use a function that is on this handout, but I'm going to go out later for the proof. Let's use this function. We're going to use this function 4x squared, in parentheses, minus 36 is on top, divided by x, what did I say? Minus 3. So what x value do you think I'm going to be interested in? 3. That kind of makes sense. Right. So I'm curious about what that limit is as x approaches 3. So if I graph this thing, now does it make sense that
I think the box is
at the end, what would the degree be if you did divide this?
one.
What degree would you have? First degree, right? So it kind of makes sense that the answer is going to be linear. Everywhere except at 3, of course, right? So here's my 3. I got to look further up, don't I?
Yes.
So let's change my window. So go to my window right here. So if you're playing along with me, have you got this here?
Yes.
All right, if you don't, you can hit zoom 6 to always bring it back to 10 by 10. That's a good starting place. But now I need to look further up, don't I? Because I don't know here's 3. Where the hell's 3 go? I don't know shit. So let's change my window. Let's change Y max so I can look up higher. Let's change it to 30. Let's see what happens. Y max so that I can look higher up on the Y axis, right? What happened?
It's the y-axis is freaking out.
There we go. What's up?
He's freaking out with the y-axis.
Oh. It's the Y-axis, dude. So now we can see 3, right? That's where we're curious about is 3. We can see the output for 3. Cool? Mm-hmm. Now, here's the neat thing. Alright, this is going to be a multi-positional problem. Crappity-doo. You can do it, Jeff. Focus. That's fine. The whole room is just tilted. Alright. So my function is 4x squared minus 36 over x minus 3. Right? And let's say somebody wants me to be... And real quick, can't we simplify this for all points except 3? So we can do it, because is our problem actually going to involve a value of 3 as an input? Because we're interested in the limit as x goes, and do limits ever get to that place? No. So how do you reduce this?
Back to the top.
Yeah, so you get 4 x squared minus 9, which is 4 x plus 3, x minus 3, and the x minus 3 is canceled. So basically that's what it looks like everywhere except at 3. Is everybody kind of with me? Right?
Kind of.
So let's say somebody gives me an epsilon. Let's say the epsilon they give me, let's start with just 0.5. Let's say somebody says, I want you to always be within 0.5 of the output, right? Of the limit, if you think that's really the limit. And what is the limit? Now when we put it like this, what is the limit as x goes to 3 of this?
24.
Yeah. Right, because now I've killed the problem, so I can just plug a 3 in. 3 plus 6, 6 times 4 is 24. So everybody see that, and that's why it makes sense. Look, it's trying to go to 24 way up there, right? So I had to put the thing up to 30 so I could see it. Maybe, okay. So here's how this works. If they tell me they want me to be that close to it, I've already plotted f of x, right? So if I do, how do I say this? if I do 24 minus 0.5 and 24 plus 0.5, so I get 23.5 and 24.5. I'm trying to recreate for you that the thing we just had from the book, where they had this, the epsilon was here, and then I'm going to try to figure out what my delta has to be. Just stay with me. So I'm going to recreate that on the calculator so I can do it myself. So if I plug in here 23.5 and 24.5, that's what somebody wants my outputs. They say, okay, if 24 is the limit, you should be able to make the outputs always in between 23.5 and 24.5 for some interval around 3. If it's not really the limit, then I can't do that. At some point it's going to be outside my box. Oh crap, then it's not really the limit. Right, so if I plot those, it's going to look a little more like the book did. And of course, look, we can't really see it, but just to bring the book back. Why is that okay? Let me bring the book back just real quick. Where are you at? There it is. So this is what we're trying to create here, right? We're trying to get the same look. So those green lines are my epsilon interval. So why can't I see it very well here? Because it's only like 0.5 apart. So I'm just going to zoom in. Is anybody playing along with me? Are you guys with me?
Yeah.
You guys got that showing up?
Yep.
Okay. So now zoom. My favorite thing, zoom box.
Oh, how funny.